Hey guys, Mr. Backward here. In this video, we're going to look at damped oscillation. Now, as we think about a sine or a cosine graph, if we were looking at the function f of x equals the sine of x, okay, this sine has an amplitude of 1, meaning that it would bounce back and forth between values of 1 and -1. But something interesting happens if we take a sine or even a cosine function and multiply it by another function. And I want to use my calculator to help me look at an example. We're going to look at the function f of x equals x squared plus 5 times the cosine of 6x. So I'm going to fire up my calculator. So in my y equals, I've got that equation typed in, x squared plus 5 times the cosine of 6x. I did adjust my window. My x min and x max I made go from -2 pi to +2 pi, and my y min I put at -40, and my y max I put at +40. Now when I hit graph, what I can see happening is the height of my wave is changing as we get closer and closer to this origin. And it's because we multiplied that cosine function by that x squared plus 5. Now if I go back into my y equals, and for my y2, if I put in the x squared plus 5 and hit graph, I can see that that parabola traces the tops of those waves. And if I look on the bottom, similar things are happening. If I went into my y equals and I go down to y3 and I put negative x squared plus 5 and I hit graph, then that graph traces the bottom of my waves. So as we see the height of our waves getting squeezed down in the middle, we call that damping. And that function that we're multiplying by, that x squared plus 5, that's called our damping factor. So the graph of y equals f of x times the sine of bx and y equals f of x times the cosine of bx, those oscillate between the graphs of y equals f of x and y equals negative f of x. When this reduces down the amplitude of the wave, we call that damped oscillation, and then we call that f of x that we're multiplying either our sine or our cosine by, that's called our damping factor. So we're going to take a look at some examples, and we're going to graph these out on our calculator, and we want to decide if these are damped oscillations. So in letter A, we've got the function f of x equals 2 to the negative x power times the sine of 4x. So I'm going to type that one into my calculator. So in my y equals, I've got that first equation typed in. I did adjust my window. My x min and x max, that's still -2 pi to +2 pi, but I made my y min and y max go from -10 to +10. So when I hit graph, so we start out with really big waves, and as we move to the right, we can see that our waves are getting shorter and shorter and shorter. So yes, this one is damped, and because it's happening as x gets larger, we would say it's damped as x approaches infinity. Now in this one, we could see the wave height getting smaller as we move to the right, so this one is damped as x is approaching infinity. Now in letter B, we're looking at g of x equals 3 times the cosine of 2x. So I'm going to type that one into my calculator. So in my y equals, I've got 3 times the cosine of 2x. I'll hit graph. Now this one we can see that our wave height never changes. It's always bouncing between 3 and -3. So because that wave height did not change, this one is not damped. So because this one had a constant wave height, then this one is not damped. And then our last one that we're going to look at is h of x equals -2x times the cosine of 2x. So in my y equals, I've got -2x times the cosine of 2x. I hit graph. And we start out with really big waves. We can see that our waves get small in the middle, and then they get larger as we move out to the right. So because the wave height is changing, yes, this one is damped. And it's as we get closer and closer to 0 from each side. So this one, the wave got smaller as we moved closer to the origin. So yes, this one is damped as x is approaching 0. Now in this example, Mr. Judge's physics class collected some data for an airtable glider that oscillates between two springs. The class determined from the data that the equation y equals 0.22 e to the negative 0.065 t times the cosine of 2.4 t would model the displacement, which we're going to call our y, of the spring from its original position as a function of time t. And the first thing we want to do is identify the damping factor and tell where the damping occurs. So as we're thinking about identifying the damping factor, we're looking for the function being multiplied by our cosine. So I'm looking at the very front of this equation where we've got that 0.22e raised to that power. So that's going to be our damping factor, 0.22e to the negative 0.065t. That's our damping factor. Now to figure out where the damping is occurring, I think it's easiest to look at a graph. So I'm going to fire up my calculator. So in my y equals, I've got that equation typed in. I do have to adjust my window. I made my x's go from 0 to 25, and I made my y's go from negative 0.25 up to positive 2.5. So when I hit graph, we'll get a picture that looks something like this, and we can see that our waves are getting smaller as we move to the right, so this one is damped as x is approaching infinity. So as far as where the damping occurs, we said that this one is damped as x approaches infinity. Now in this part, we're going to use the exact same information, but we want to figure out how long it takes for the spring to be damped such that the y values, so the oscillation height, will be between negative 0.1 and positive 0.1. So I'm going to look at a graph again, but I'm going to add in a couple extra pieces. So in my y equals, for the y2 I have that negative 0.1 plugged in, and for the y3 I have 0.1. When I hit graph, that's going to add in some parallel lines, and what we want to do is find the time when our entire graph is between these lines. So I'm looking at the bottom of this wave in the middle. It looks like my blue line is intersecting my red line, but after that it looks like my blue line is entirely between these lines. So I want to figure out where this intersection point is happening. So I hit second trace, and I want to do intersect, so that's option number 5. I'm on my blue curve. I want that to be my first curve. And I'm going to arrow left a little bit. I hit enter. I switched over to my red equation, that y equals negative 0.1. So I hit enter, enter, and it tells me that those intersect at about 11.68 seconds. So after 11.68 seconds, then our oscillation will be between that 0.1 and that negative 0.1 that we were looking for. So he said that it would take approximately 11.68 seconds to be damped so that our height is between the negative 0.1 and the positive 0.1. That's going to be it for this video. Thanks for watching.